All right, so welcome everybody to the Summer 2016 version of our student exit presentation. So this is group one. There will be more to follow. So our next presenter is Deegan Atha, who joined us for the second semester, right? He's from Purdue and is becoming an expert on robotics and computer vision systems. And please welcome Deegan, who's going to talk to us about the eponymously named 3 Deegan effort here in the Autonomy Incubator. So please welcome Deegan.
So as Danette said, I'm Deegan Atha. I'm a rising senior at Purdue University studying computer engineering, and I'll be talking about object detection and classification. So this is my Agile quad chart. So my objectives are to develop an onboard system of object detection and classification, develop an internal data set to train our convolutional neural network to do this detection and classification, as well as identify where these objects are in real-world space, not just in an image frame, and then test this in indoor and outdoor flight. So a couple milestones over here. We're to update a CNN from the fall to the summer as more research has been done in that time frame. Create LiDAR, stereo, depth calculations, create the internal data set, do some fun facial classification, as you'll see here, and then also integrate with Spiderbot and some tracking. So the motivation for this work is, one of the main reasons is to develop robust safety maneuvers. So if you have a pole or a tree, the maneuvers that a drone would want to take are different than if you were to encounter another drone, because a drone can move and it can move around in space. A pole is stationary. So a pole you can go directly around. Another drone you would want to take a wider path around it. Furthermore, you can have expanded applications for these UAVs. So for package delivery, you can identify packages that you've trained on, go to those packages, pick them up. Search and rescue. If you are looking for a person or a boat, you want to be able to identify what those objects are. And then with science missions, you can use this capability to, say, follow the drone. And if the drone can know what another drone is, you can integrate those two things, or even integrate these objects into a VR realm. So a high-level overview of convolutional neural networks. You'll hear me say that word throughout the presentation. Basically, what this network does is it learns features and then creates a hierarchy of these features and then identifies what that hierarchy of features represents. So if you were to have a car input into the network, you would learn some of the low-level features first. There's a circle right here. There's an oval here through the first layer. And then as you pass through more layers, you combine those features together. So then you learn there's a circle with a more oval object here. And then at the end, you have a hierarchy of these features, and you say all of those features combined are a car. So the more layers you have means the network is deeper, and it's more accurate, but it's also more computationally intense and slower. So there's a trade-off between the two. In the fall, I worked with the ASUS Xtion RGBD sensor. So this has red, blue, green, as well as a depth value in the point cloud. And to detect objects, I used Euclidean segmentation of the point cloud. So if the points are close together, they are an object. I took those coordinates and passed them into a convolutional neural network and classified those specific regions and mapped them back to the point cloud. So you can detect objects in three-dimensional space here. This was running partly on board the NVIDIA Jetson, as well as some of it still had to run on a desktop because it was too computationally intense. So that was one of the main issues. The second main issue is the ASUS Xtion is an indoors-only sensor. The outdoor sunlight can wash out the IR sensor. So this summer, Faster RCNN is a recently published and released algorithm that I began integrating into the system. And so what this algorithm does is it integrates a regular convolutional neural network with the region proposals, the detection aspect of the algorithm. So you can have a regular convolutional layers that detect all the features within an image frame. Then you pass those features to a region proposal. So you would say, these features right here could be an object. Then in the last layer, you say all these potential objects and their specific features, does it represent something? So is this region a car, a person, or is it nothing? And so this can be used with different network designs. So two of the main ones that were looked at were the VGG16 and the ZFnet. So the VGG16 has 16 layers, the ZFnet has 8. So ZFnet is faster, but it trades off a little bit of accuracy to the VGG network. And the ZFnet was able to run at 20 frames per second on the Titan X on a desktop computer. And on board the NVIDIA Jetson TX1 board, which was released in December, it ran at 2 frames per second fully on board. So there was no separation between the two as in the fall. Another aspect of the project was to create a training set for our purposes here at the Incubator. So as the base data set, the VOC 2007 detection data set was used. So these images were in semi-clustered environments, real-world settings, so you could have a person, a car, all in one image frame, and it had bounding box with that. So I added additional images to some classes there, as well as added further classes that had no images or bounding boxes for things that we would like to detect, such as drones, trees, poles, balloons. There are now 19 classes in the main data set. Some different models have more classes. Some have faces, some have packages, trains. But in the base data set, there's 19 classes. There's also a simplified process to add more images and objects to the data set. So this is a dlib annotation software right here where you can bound objects. And then I've created scripts that convert the output of this program to the format needed to train, as well as easy ways to update your training, validation, and test sets. So the next step was to calculate the depth and know where these objects are in real-world space. So in the fall, that was with an RGBD sensor and segmenting out these objects in 3D. But this sensor is not going to work outside. So we looked at two main approaches. One was stereo with cross-correlation, which calculates the shift between two images. The other was to calibrate a 2D LiDAR with an RGB camera. So you get the translation and the rotation between the camera and the LiDAR, and then you can map the points back and forth between the two. So for stereo, it's computationally intensive to recreate the entire point cloud from two images. And with the convolutional neural network already taking up the full power of the GPU, that would be a pretty big slowdown. So we looked at cross-correlation of cropped objects within an image. So if a person was detected right here, we would crop that person and then crop that same area within the other image frame and then try to calculate the image shift between these two. And so this worked okay when objects were fairly close up, but as you move further away, oftentimes the object would be cropped more than what would be needed to calculate the shift, and so the accuracy was severely limited to a range of about only a meter or so. So that was not pursued much further than that. The next thing that I looked at was LiDAR and RGB. So this, we already have a LiDAR node that detects and tracks objects in the world. And so this was just simply reading the DDS objects and matching those objects back to the bounding box images after the calibration between the two. So if you have a bounding box right here, and a LiDAR point can be translated, and it would fall somewhere, hopefully in the center of the X range. And so whatever point is closest to this center line right here would be the object in LiDAR space, and it would be correlated to the object in the pixel space. So then that LiDAR object would be a person in this case. And then this is a quick video of this value right here is the distance in meters changing as TN steps backwards. Okay, so then in this video, TN is stepping back and the number in the top corner is changing and is increasing, and that is the value in meters of how far away TN is. This value we've seen, or I've seen it be accurate to about 15 meters. I've been able to detect people and match the two. So then with this node, we want it to be portable so that it can be used by other nodes within the AON system. So two of them that are currently using it is LiDAR mapping, as well as the Spiderbot package identification and tracking. And in the future, this can be VR visualizations so that if a drone were to see a person at whatever world coordinates, a person could appear in a VR simulation in that same distance relative between the two coordinate systems, as well as in-flight decision making. So if you were to see a person versus a pole, you could do different maneuvers. So LiDAR mapping here. This is our current map of what the drone would see with the LiDAR. So there's an object right here. The drone identifies that object and plans a path around it. But right now, we do not know what that object is. So if you integrate the LiDAR in the classification, we can now know that this object is a drone in the case of this snapshot here. And this object can be continued to be known outside of the field of view of the camera as long as the LiDAR continues to track that same object. So there's an object, it's detected by the LiDAR, it then enters the field of the view of the camera, is classified, then it leaves the field of the view of the camera but is still within the field of view of the LiDAR and is still identified as a person. So the second one was Spiderbot. So we can train on anything as a package. This package can be a ball, as in the case of this video. It can be a box, just anything we want that we have images of, as well as bounding boxes. And then we can use the camera to locate and track these objects so that the Spiderbot can move and pick up these objects. So this is useful for environments where it would be difficult to land precisely and pick up an object. So you could land next to an object, track to the object, and then pick it up. And this also allows for us to be able to have the package in orientation with no need for any external markings. So you don't have to have any QR codes or anything like that. You can just have any package object, go to it, identify it, move to it, pick it up, and bring it back to the drone. So it allows for much more general package pickup mechanisms. So in this video, the Spiderbot will start tracking towards the package. It will identify the package, and it will start moving towards the package until it finds the package and stops moving. So then one of the last things that I was working on was tracking within the image frame. And so this would occur in a separate thread from the convolutional neural network. So running on board, the convolutional neural network takes about 500 milliseconds to run. So there is a lag between the image frames and then where the drone would actually be looking in real time. So what this would allow is that you would classify an object and then immediately in real time run a much faster tracking algorithm to track to those classified objects where they are in the current image frame. And then you could continue to track the objects while the next round of classification occurs. So this would allow the drone to appear to be detecting and identifying objects much closer to real time. Along with this, I had created a Python wrapper for a library that was published in the 2015 Detection Challenge. However, this was interrupted due to the flooding, so it's not been tested that well on board. But there is a demo of it running on the desktop, so you can see it running and its speed. So the convolutional neural network would create that bounding box, and then as the image moves, it would continue to track that object and it tracks pretty accurately. So then this would allow for more quick and more information being sent to things such as the Spiderbot. So the Spiderbot would not have to wait 500 milliseconds to keep identifying where the package is in the image frame. So one fun little side project that I worked on was creating a facial library for most of the people in the incubator and classifying them as their nicknames. So you have Ben Kenobi, 3 Deegan, Superman is Javier, Paul is the target. He was afraid of it, so it was an accurate name. Sexy Hips and Dr. Drones right here. And there were more. But this did have some practical learning based with it, because the more faces that I added to the network, the accuracy severely declined. And this is because the network is not as deep as some other networks. And so all the faces look fairly similar at a higher level. And so when you cannot extract as deep of features, it becomes harder and harder to distinguish between different faces without having the deeper features. So if we are going to try to train on multiple different types of packages that are all fairly similar, we might see a decline in detection and classification accuracy from that. So future work is flight integration for testing indoors and outdoors. It's ready and built on a quad. Just with the flooding, we had to delay some of that testing. And then I'd like to see this integrated with VR, so that if you were to detect a person, that object could appear in the VR world for the viewer to see what the drone is seeing. So acknowledgements, I'd like to thank the entire incubator team, as well as the education office. And a special thanks to Dr. Lak-Tran, my mentor, Dr. Nadalan, Ben Kenobi for his wisdom in the ways of the Force, as well as Python. Carol for setting up many different events for the interns and buying things for me, as well as Tien, who did a lot of the bounding box work for me. So thank you, Tien.
Great.
Any questions?
How does the network look for features? Is it looking for specific features like eyes, or is it looking for geometric shape?
Okay.
How does that work?
So the network is not looking for any specific features that I tell it to look for. It looks at the region and it tries to learn what features exist in this region. So if there's changes in pixel values between 2 spots, the first level might learn to be an edge detector. Then another, and so there are several different filters at one level. You could have 128 different filters in one layer. So one might learn to be an edge detector, another would learn to look for high concentrations of red or high concentrations of blue. And then as you go, it combines those features together to create a hierarchy of them. So it's attempting to learn what it needs to look for, as well as what the objects are. Yeah.
Just curious, for no particular reason at all, the LiDAR portion of it, where you tie up the LiDAR points to the camera, how well did that work?
It worked pretty well. The calibration was a little iffy, but a few manual tweaks, it worked pretty well. And so then the biggest issue is if there were 2 objects within a similar bounding box. So if someone was holding a drone and then there was a person, you'd have 2 overlaid bounding boxes. So being able to identify the 2, which object was which, was difficult, but you would still know the distance of one of them. But if there was just a single bounding box in the image frame, they matched pretty well, and the distance was known most of the time. So, yeah.
All right, so Deegan, when you're creating the internal data set, how many images do you need to create a classification or a new classification? And how does that relate to images that are loaded from the previous or the data set that you downloaded? And do you do anything to prevent overfitting, where if there's one data set that, or one classification, like one class, like a person who has lots and lots of different images, whereas our drones only have maybe tens of images?
So I'll start with the first question, which was the number of images per specific class. So the number of images for most of the classes was around 300 images. For people, the number was significantly higher, it was about 1,200. And this relates some to the variations between the objects. So for people, there's many different types of people, many different poses that people could be in. People would be, half the person could be in the image frame. So you need more images to learn all the features that you could see in the real world. For the package, it was just a blue ball. It was always going to look fairly similar across many different angles, so you can get away with fewer images to train on that. And then, so the question is about overfitting for if you have more images of people that might dominate the classification, so you might see people being classified more than what they should be. So no, not currently, but there are ways to, I do save the model snapshot at a number of different iterations. So if you train over time, you can overfit at different points. So I do try to pick the most accurate iteration number across there, but I don't do anything specific with the data set at the time to try to limit that.